Hey guys, so today I'm going to be going over L'Hopital's rule for composite exponential functions, or what some people also like to call a instance of the limit chain rule. And so the type of question that we usually encounter is where we have a limit and x is approaching a value a, and then the function that we're evaluating has two parts to it. The base, which is raised to the power of a different function, g of x. And normally, or not normally, but often, you can plug in your a value and that'll be the end of the story. But more often than not, there's going to be an issue when you're trying to evaluate this, that you'll get something of the form of 0 to the power of 0, infinity to the power of 0, 1 to the power of infinity, or another indeterminate form. And so the issue is that we don't know what these are equal to. But usually if this is on a test or an assignment, you can rearrange these indeterminate forms to make it so that you can get an actual numerical answer. And so the way to do that is to take these indeterminate forms and then transform it using a method I'll show you into a L'Hopital form, which is 0 to the power 0 over 0 or infinity over infinity. And the thing to note with this as well is that when I say infinity, this can be plus or minus infinity in each scenario throughout this video. And so the thing with this then is once you have it in this L'Hopital form, you can actually take the function that you have and perform L'Hopital's principle on it, which will then hopefully give you something that you can actually manipulate to get a actual answer. And so that may seem vague, so we're going to do some examples in this video, and I'll also walk through this example here. So let's continue and assume that this example does give you something in this form. What I'm first going to tell you to do is write a let statement that just says let y equal f of x to the power of g of x. You don't always need to write this let part, but I sometimes do just to clarify and to point it out. So here is our first statement. The next thing that we're going to want to do is take the ln of both sides. And this may seem confusing right now, but once we do some examples, you'll see why we need to do it, because we need to transform our indeterminate form into this L'Hopital's form. And remember from our log rules that you can take the exponent of a log argument and move it to the front of that argument. So we can also write that g of x ln f of x is also equal to ln of y. And so now we're going to raise both sides to the power of e. And the reason why we do this is because raising e to the ln of any constant or function is just going to return that constant or function, like so. And so in that way, we're going to end up with y on the left side of our equation, like so. Y equals e to the power g of x ln f of x, where this g of x ln f of x is in the exponent of the e. And so now what we can do is we can actually put this y back into our limit here. And so I'll show you just by clearing up some space here. So we can write that this limit is actually equal to the limit as x goes to a for e g of x ln f of x. And I'll write this in brackets again, just to clarify that the f of x is part of the ln. And so you may say, well, this doesn't look at all like what I have over here, but these are equivalent statements because we did this whole process to get there. And so the next thing that we need to do after we have this is apply L'Hopital's to this statement if this function in the exponent above e gives us that indeterminate form of either 0 over 0 or infinity over infinity. But before we do that, the next thing that we need to do is move our limit into the exponent position. And you may say, I've never seen a limit in the exponent position. And that's because we don't do it that often, but you actually can do it when the base is a constant. Because when you think about it, this limit is saying as x approaches a value a. And so all that's changing according to this limit is the x value as it's approaching a. So we don't actually need to include that in front of the e. The e is a constant, so we can just move the limit into the exponent, and so we can write it that these two limit statements are also equal to e to the limit x approaches a for p of x ln f of x. And at this point, we're going to assume that this function would give us these indeterminate forms, one of them. And so what we would then write is L'Hopital's rule over the equation, just a little h to denote that we are doing it. Then we would perform L'Hopital's rule on this part, the part I'm about to highlight in blue, of the limit, and that would hopefully allow us to evaluate the rest of the equation to an actual numerical answer once we apply the limit. And if that seems confusing, it's okay. It'll make more sense once we do examples, hopefully. And so I won't do that because it's difficult to show taking L'Hopital's rule on some imaginary functions here, and I think it would just be confusing. But as a brief review, I will just go over what L'Hopital's rule was. And so L'Hopital's rule states that if you have a limit as x approaches c for a fractional expression, then if we take the derivative of the top and the derivative of the bottom, that these two statements will then be equivalent, like so. And so this is L'Hopital's rule stated. Okay, so that's great. Let's now get into some examples. So the first question we're going to attempt here is the limit as x goes to infinity, x to the power of 1 over x. And let's say that we're asked to evaluate this. And so the first thing when doing a limit that you should always check for is if you can just plug in your values. And when you just try to plug in your value, you're going to get infinity to 1 over infinity. And 1 over infinity is actually 1 over a very small number, which is actually approaching 0. And what I mean by that is if you think about it, let's say you have 1 over 1, that's just 1. And 1 over 2, that's 0.5. Then 1 over 3, that's 0.333. Then 1 over 1 over 4 is 0.25. And if you keep going, you keep getting closer to a smaller number. And so eventually you'll get 0. So 1 over infinity is actually equal to 0. So you have infinity to the power of 0, which is an indeterminate form. And so that should be a clue to us that we can start with the steps that we previously discussed. And so the first step that we discussed was letting y equal to the inside function that you're evaluating, right? And then the next step that we talked about was taking the ln of both sides. And then the next step was to take the exponent function and bring that out to the front on the right side. And this is still equaling ln y. And then our next step was to raise both sides to the power of e. So if we raise both sides, that just leaves us with y on our left-hand side, and then e to the power of 1 over x ln x, right? Which can also be written as e ln x over x. And our next step in this was to put this y back into our limit. So we can then write that our limit, as x goes to infinity, for x 1 over x is also equal to the limit as x goes to infinity for e to the ln x over x. And so our next step here was to take this limit and move it into the exponent position, because the e is actually a constant and x is the part of this function that is actually changing. So we can then write that both of these are equal to e limit as x goes to infinity, this is in the exponent position, for ln x over x. And if you try to plug in your infinity again, what you get is something like infinity over infinity, because ln of infinity is infinity. And so that means that we can apply Hopital's rule, because we are always trying to get our function into the form of 0 over 0 or infinity over infinity. And so what we then have is little h above our equal sign to denote that we are now going to apply Hopital's rule just inside of this function. And so the derivative of ln x is 1 over x, and the derivative of x is equal to 1. So we can then write limit as x approaches infinity is then 1 over x over 1, right? Because we took the derivative of this top function and the derivative of this bottom function. And so that is simply 1 over x over 1, or just 1 over x. And as we talked about previously, when you have a limit as x is approaching infinity for 1 over x, your answer is going to be 0. So we can actually replace this limit, 1 over x, as x goes to infinity, with 0, which is e to the 0. And any number raised to the power of 0 is 1, and e is a number, remember, 2.7, yada, yada, yada. So our final answer is 1. Okay, so let's now try another problem. Let's say you have the limit as x is approaching 0 from the right for the function tan of x, and I'll put this in brackets again, to the power of x squared. And so if you look at this problem, right, tan of 0 is going to be 0, and then 0 squared is still 0, so you end up with the form of 0 to the power of 0, which is an indeterminate form, so that should be a tip to you to start with these steps that we had discussed. And the first step was to let the function of the limit that you're evaluating equal to y. So we're going to write y is equaling tan x to the power of x squared. Our next step is to ln both sides. So ln of y equals ln of tan x to the power of x squared. And then our next step, I'll make this a square bracket, just to be clear. And then our next step was to bring this x squared out in front. So we are going to have x squared ln of tan x. And on this side, we still have ln y. And then we are going to raise both sides to the power of e. So that makes the left side just equal y, and the right side e x squared ln, and I'll write this in parentheses now instead of brackets, tan x. And so our next step after we have this e form is to put this y back into our limit. And so I will just clear this away. And so we have this limit is also equal to the limit as x goes to 0 from the right. And then I'll put in brackets e x squared ln of tan x. Right, and so that is our limit. And then our next step is to move that limit into the exponent position, which we can do because that's where our x's are, and our limit is just saying that the x is approaching 0, so this constant is just going to stay as the base, so we can then write that this, I will clear up our board a bit here, we can then write that this limit is also equaling e to the limit as x goes to 0 from the right. And then we will have x squared ln of tan x. But if you try and plug in 0 from the right into this function here, you're still going to end up with a indeterminate form. And so what we're actually going to do is I'm going to multiply this function by 1 over x squared to move our x squared into the denominator. And so I'll show you what I mean by that by actually doing it. And I'm just going to erase this parenthesis temporarily. So let's multiply this by 1 over x squared, and then 1 over x squared, and then end up having a 1 over x squared in our denominator. And so this now equals e to 1 over x squared. And this is, of course, all in brackets. And so the next thing that we need to do is look at what form this is going to give us. And this is still going to give us something of the form of infinity over infinity, which means that we can then apply Hopital's rule here, because as we have infinity over infinity as the form, and we're just applying it inside this parenthesis here. So if we apply that, we do the derivative of the top, the derivative of ln tan. What we need to do is say the derivative of the outside using our change rule, which is 1 over tan x, and then the derivative of this tan x is secant squared x. And so we know the derivative of the top, and then the derivative of the bottom, 1 over x squared, is equal to -2 over x cubed. And so then what we can then do is plug that back into our limit. So I've written the h here to denote Hopital's again. Brackets here, a little bit bigger to be more proper. And even though it can get confusing, remember that this whole limit, and by default then this whole function inside the limit, is all raised to the power of e. So we now have that, and what we then want to do is try to clean it up a little bit, because it can be confusing to try and plug in 0 to this big hot mess. I'm just going to clean up the board a bit here. And so what we are now going to do is clean it up a bit. So we are going to set this equal to, and then e to the limit as x approaches 0 from the right. And then using our fractions, we know that we can write this as x cubed secant squared x over -2, something of the form of 0 to the power of 0, or 0 over 0 again. And so you may say, oh, well, now does that mean I have to apply Hopital's rule again? And unfortunately, you do in this situation. So we're now going to apply Hopital's rule for the second time. So we'll put h and then just 2 down, and then we will do Hopital's rule for the second time by determining the derivative of the top and of the bottom. So the derivative of the top is x cubed secant squared x, using our chain rule, becomes negative x cubed 2 secant x multiplied by secant x tan x minus 3x squared secant squared x. So this is all on one line here. It's just very long. And then our derivative of the bottom, I'll just clear this so we have some room, is then equal to the derivative of -2 tan x, which is equal to 2 secant squared x. And so then what we're going to do is plug those into our limits. So we then have e, this is going to be super big, x, as x approaches from the right. For your limit going to the right, you'll actually end up with the form, well, not the form, you'll actually end up getting e to the power of 0 over 2, which is actually just equaling to e to the 0, which is actually just equal to 1. So your final answer is 1. So let's take a look at our final problem. And the final problem is limit as x goes to infinity for the function x plus a over x minus a to the power of 5x. And we are being asked to evaluate this. So when we're dealing with limits, as we've done in our other examples, the first step is always to try and plug in our values straight away. And if you try and do this, what you'll end up getting is infinity plus a over infinity minus a to the power of 5 times infinity. Now, there may be a few questions you have right now. First of all, you may wonder, okay, what's this a? And in questions like this, you can usually assume that a is a constant. And if not, the question should state otherwise. So what we're saying is we're adding a constant like 5 or 6 or 7 or whatever number we want, or subtracting it from infinity. And so when you're thinking about this, what you really need to consider is, can I subtract or add or multiply a number by infinity? And the answer to that is not really, because infinity is a concept. If you were to point at it on a number line, you couldn't, because it's the biggest number there is. So if it's the biggest number there is, by definition, if you subtract a little bit from it or add a little bit to it or multiply it by something, it's already the biggest number. All of those changes are inconsequential. They don't really matter. So considering that, when you're writing the form, you can really then write it as infinity divided by infinity to the power of infinity. And it's important to note that you can't just cancel out these infinities here. That would be incorrect. Even though you would still get the indeterminate form of 1 to the power of infinity, you can't divide infinity by infinity, because infinity is just a concept, not an actual real number. So when considering this, this is a indeterminate form, even though it wasn't one that we originally talked about. So that means that we can apply the same steps that we've been using. So as we've been doing, the first step is to let a variable equal the interior function that we're applying the limit on. So here I'm going to let y equal x plus a divided by x minus a, and I'm going to make this x just a little bit clearer, and same with that a, to the power of 5x. Then our next step is to take the ln of both sides. Then our next step is to bring this exponent into the front using our log rules, and this is still equal to ln y. And then our next step is to raise both sides to the power of e, and that will leave us with just y on this side. So we will have y equaling e to the 5x ln of x plus a over x minus a. And so now we can put that y value back in to our original equation, or our original limit rather. So this limit is also equal to the limit as x goes to infinity for e to the 5x ln of x plus a over x minus a. So now we're going to need to, as usual, try again substituting our infinity in. But if you try that again, we're going to get 5 times infinity ln of infinity. And so that's still an indeterminate form, so we're still going to want to try to manipulate this into getting our L'Hopital's form so that we can hopefully get an actual answer. Okay, and then our next step is to move this limit into the exponent position, and I'm just going to clear up the board a little bit here. And so we're also going to have this equal to e to the limit as x goes to infinity for 5x ln x plus a over x minus a. And so when trying to substitute this in, we're still going to run into the same problem as earlier, that's an indeterminate form. And so what we're now going to do is the same thing as in our previous problem when we're trying to get it into the L'Hopital's form, which is to multiply by 1 over x. So I'm just going to erase this bracket here so I can do that. And I will write that we are multiplying it by 1 over x and 1 over x. And so what happens now is that these x's cancel, and we now have the equation e limit as x goes to infinity 5 times ln x plus a over x minus a over 1 over x. And this is in brackets and all in the exponent of e. And so if we consider this again, we're going to have something of the form of 0 over 0, which now means we can apply L'Hopital's rules. And I'm just going to clear up the board a bit here because we're going to have to do quite a bit more. So when applying L'Hopital's rule, we're going to need to take the derivative of the top and the derivative of the bottom. So to take the derivative of the top, we're going to need to take the derivative of ln x plus a over x minus a. And that means that we're going to have 1 over x plus a over x minus a, and times the derivative of this, which is x plus a over x minus a, which is then going to be, if we simplify this in our next step, x minus a over x plus a. And then in this situation, we're going to have to use our quotient rule, which will end up giving us multiplied by x minus a minus x minus a all over x minus a squared. And these two x's are going to cancel out. So then what we end up with is x minus a over x plus a multiplied by negative 2a over x minus a squared. And so I'm just going to remove this from the board. Okay, so now we also need to determine the derivative of 1 over x is also equal to the derivative of x to the negative 1. And recalling our power rule, if we subtract from the exponent here, we're actually going to get negative x minus 2 because we have to take the exponent that we had before and move it out to the front and then subtract 1 from this. So this is going to be our derivative for 1 over x. And then we have our two derivatives, so now we just need to plug that in. So here I'm just going to write an h to denote Hopital's rule. And so what we now have is e to the limit as x goes to infinity for 5 outside of the limit, because 5 is a constant on the numerator, so we can just take it out. 5 doesn't depend upon x because it's just a constant. And so we are then going to write all of our derivatives. So the first one is x minus a over x plus a multiplied by 2a over x minus a squared, that binomial. And then we're going to have that all over negative x to the negative 2. And so now that we have that written down, I'm just going to clear up our board a bit here. This is a really complicated function inside of our limit, so let's see if we can clean it up a little bit. So we're going to start by multiplying our fractions together. So this is going to give us e5 limit as x goes to infinity. And then that is going to give us negative x squared with x minus a minus 2a, all on the numerator. And then on the denominator, we are going to have x plus a and x minus a squared. And so what you'll notice here is that we can then cancel out these two factors, well, just the top one, and then take away the squared from the bottom one. And so what that further leaves us with is equaling e to the 5 limit as x goes to infinity. And then these negatives are also going to cancel. So we're going to end up with 2a x squared on top divided by x plus a, x minus a. And now we are going to be able to even further simplify this, because if you look here, that looks like a perfect square. So we can even write this as e to the 5 limit as x goes to infinity for 2a x squared all over x squared minus a squared, right? And our next one that we are going to do is further simplify this, because if you look at it, we still have the issue of having a indeterminate form. So we can actually multiply the numerator by 1 over x squared and the denominator also by 1 over x squared. And that will also give us e to the 5 limit as x goes to infinity, which we've written a bunch by now. And then this is going to cancel out the x squares on the top. And so then on the bottom, we're going to have, well, on the top first, we're going to have 2a, and then over x squared minus a over x squared. And then further, we're going to be able to simplify this. So we can then write this is equal to e 5, the limit as x goes to infinity. I'll make this n more like an m, and then 2a, and then at the bottom here, we're actually going to be able to rearrange this into 1 minus a squared over x squared. And the reason that we can do that, of course, is because this fraction here, x squared minus a squared over x squared, can also be written as x squared over x squared minus a squared over x squared. And so if we simplify that, these will cancel, giving us just 1 minus a squared over x squared. And I will just clean that up a little bit. And so over here, this is the limit that we have, and then we're going to want to see if we can evaluate that. And so what we can actually do is just apply our limit to where our x is. And if you see, we only have one x now, and that's over here. And so what we're going to do is say, okay, well, a is a constant, so we just have a constant over an x squared. And the limit as x goes to infinity for a constant, we can call it a squared if we really want, over x squared is equal to 0. And that's for the reason that if we have 1 over 1 squared, and then 1 over 2 squared, and then 1 over 3 squared, these numbers are going to keep getting smaller and smaller until we get to 0. And so considering that, I'm just going to clear that up a little bit. So we can now rewrite this as e to the 5, and then 2a, 1 minus 0, because we've applied our limit. And so that, of course, is just equal to e to the 10a, which is our final answer for this question. So hopefully that helped you guys, and I hope you understand a little bit more about applying L'Hopital's rule to composite exponential functions.